So I'm Peter MacKenzie, and I'm a director of services for ThinkBig Analytics. That's the consulting arm of Teradata, and I lead the AI and deep learning team. And so I'm going to talk about deploying AI in the fight against financial crime. And I'm going to start, I'll kind of give you a bit of an overview of the problem, and then I'm going to go into some fairly technical, I wouldn't say technical, but details about how we use AI in order to fight fraud. And I'll talk about a use case. Just out of curiosity, how many people have done any work with AI in their jobs, either data scientists or training or project leads or, okay. Just a few people? Yeah. And how many are actually involved in financial crime or fraud? Okay, good. How many are, what's that? As a good guy. Sorry, thank you. Thank you for the clarification. Yeah. For those who are actual criminals, then can you please move over to the side of the with banks? Yeah, mostly banks. Okay, good. All right. Well, let's get started. Just a quick word about Teradata and ThinkBig Analytics, just so you know who we are. I think a lot of you are probably familiar with Teradata as an enterprise data warehouse company. ThinkBig is the consulting arm of Teradata, and really our mission is to help companies build analytic solutions on a scalable data foundation. And that includes HDFS, it includes relational stores, it includes object stores. ThinkBig, we're business-led, technology-enabled. We have lots of experience with open source as well. And we've been doing more and more projects with customers using AI. So things like enhanced car navigation systems. We did a project with one of the largest suppliers of auto parts. And we've done fraud detection, which we're going to talk about today, intelligent process automation, chatbots, things like that. So just a little bit of groundwork here for those who are not actively involved fighting financial crime. This is a really significant problem. We're really just touching the tip of the iceberg in terms of what we know of financial crime and the types of threats are out there. And actually, a little bit of a statistic here. According to the UN report in 2017, financial crime yields about 1.6 trillion annually, which is pretty staggering. I'm from Canada, and I guess that's pretty close to Canada's GDP. I almost find that hard to believe, of which only 1% is caught. And catching that 1% is costing banks about $50 billion per year. So that's a pretty serious problem. And then the threats are coming from not only your hackers and your criminal organizations, but nation states and terrorists and insiders within your organizations. Actually interesting that AML in particular, I don't know if you've ever gone to an AML conference, but it's really a call to action because a lot of that is funding weapons trades and human trafficking, and there's all kinds of horrible things. So fighting financial crime is the front line to stop some of that nastiness. And of course, in terms of banks and the cost of it, there's not only the monetary loss, disrupts your business, loss of reputation, which is a biggie. It's hard to put a dollar value on that. Loss of public confidence, it's a big problem. It's a bad problem. I think we can all agree on that. So I do want to just kind of lay out, some different types of financial crimes, and we don't need to debate this, but broadly, 4 kind of categories. Payment fraud, so we're talking about credit card transactions, online payments, things like that. AML, a little bit different, anti-money laundering, of course. Cyber crimes, more general, attacks, intrusions, things like that. And then insider threats, which are, manipulation within the organization to commit crimes, whether it's, rogue traders and things like that. And I kind of point that out because what I'm going to talk about, some of the use cases I'm going to talk about, is really more around the payment fraud. And each of these approaches have kind of different types of analytics that you might do. For example, AML with networks, definitely you're going to do some sort of graph analytics to find networks. With payment frauds, a lot more transactions, which is a great data source to be able to do time series analysis and try to predict behaviors. And that's some of the work that we've done. Just a little bit more on the problem. Obviously, the industry isn't keeping up. The fraudsters are just very fast coming up with their schemes, literally changing overnight. And so most banks have rules engines, and so they're manually creating rules. They're manually identifying trends, and they're creating rules to stop them. And I'll just say right now that the work that we do, we're not talking about replacing rules engines. What we're talking about is augmenting rules engines. So using machine learning and deep learning to come up with other scores that we can incorporate into your rules engines. But the rules engines, they're good at finding certain types of fraud. And I think I'm gonna make the distinction to say like global fraud versus emerging fraud. So there's some things that are kind of static, and it's very easy to create a rule and very fast to stop it. Machine learning is good at the emerging, the new schemes, and be able to pick up those trends much faster than, say, a human can look at it and come up with the new rules. So that's really the advantage of using machine learning and an AI. And sort of another point I'll kind of get into is that this distinction between machine learning and deep learning. In fact, I'll just say it right now. So, when I talk about machine learning, it's sort of a broader case. Where deep learning, I'm talking more about using neural nets in a certain class of machine learning. And machine learning can be very effective as well. And then we'll talk a little bit more about how deep learning is different and the types of crime it's particularly good at finding. Anyhow, rules engines can't keep up. AI is very fast at evolving and catching these schemes. And this is just a case study. I think we've been talking about it, for a while. We've done some other projects with other banks, but it's kind of a good example. And it might be typical of your businesses, I'm not sure. But they weren't able to detect 60% of the fraud. And then 99% of the transactions that they were flagging as fraudulent and spending money to go investigate weren't actually fraud. So that's costing a lot of money. I think actually their investigators were probably a bit overwhelmed, and at a certain point at the end of the day, they just, okay, that's good, and move on. So they were looking for a partner to help them solve this problem. And so what we did was we went in and we tried a lot of different machine learning and deep learning approaches in order to be able to detect more fraud. And we also helped them engineer it because, as you're probably aware, when you're talking about at least payment fraud, and you want to integrate with your authorization system, you have pretty strict SLAs. So you're going to want to be able to make a decision pretty quickly, which requires some pretty special architecting. So we helped them with that as well. The net result was that we were able to increase the fraud detection rate by about 50%. And so that's obviously saving the money right off their balance sheet. And we're also able to reduce their false positives. So less time spent having investigators go and investigate different transactions. I'm going to start to get into more details now, but first a little bit of a point just to talk about deep learning, and this is sort of our observations of having done this for a while. But deep learning, a lot of the breakthroughs that we've seen in deep learning is in the areas of computer vision and sound and speech recognition and NLP. And in fact, some of the characteristics of that is the kind of data. The data is much more uniform. And so when we talk about fraud and some of these other problems that we've traditionally used analytic approaches like machine learning, the data is not like that. So it's kind of a question as to whether or not deep learning is better than those other approaches. And so there's certainly advantages. We've seen with deep learning, more data, bigger models, more computation, generally you see better results. And I don't have the slide here, but you've probably seen a graph, or maybe you haven't. But machine learning, as you apply more data, deep learning and machine learning models sort of perform the same to a certain, at the beginning. And as you apply more data, the machine learning models sort of just plateaus out. But the deep learning models just get better and better. We're able to perform even better with the more data. So in the case of fraud, when we have transactions, you're going to have millions of transactions. It's actually quite a lot of data. Some of the And then, so another advantage people talk about deep learning is, less feature engineering, which is true if you're doing image detection, because it's just all pixels. But if you're trying to solve problems, business problems that say, like fraud that has transactions, it's not true, and I'll get into that in more detail. You still need to do the same kind of feature engineering that you might need to do for machine learning. I'll get into those details later. Some of the disadvantages of deep learning is, well, it requires a lot of data, and it requires a lot of compute power, and it's also sometimes difficult to interpret. And so I think some of you probably have heard of the fact that it's like a black box, and the neural nets have multiple hidden layers, and we really don't know exactly what it's doing, which can be a challenge for some of the interpretation or audibility. If you need to come up and say, hey, I did not give this person an increase in their credit rating because of, you need to know a reason. So there are tools, and there's a lot of work in this area, things like LIME and SHAP, that are trying to solve that problem of interpretability. I think I talked state of the art, computer vision, NLP, reinforcement learning. I'm just kind of showing here, same point I kind of made before. Some of the things that deep learning is good and we've seen breakthroughs in are things like image detection, reinforcement learning, language, where generally humans are good at it. The data is uniform, and there's also an abstraction. If you think about images or recognizing a face, it's made up of lines and shapes, which makes up noses and eyes and ears, which we know as a face. So there's a hierarchy in there. But with transaction data, well, people aren't generally good at looking at transaction data and picking out patterns. There's no obvious hierarchy in the data, and it's very heterogeneous. You've got transaction amounts, you've got locations, dates, merchant categories, and so forth and so forth. So it's not entirely clear that deep learning would be better at these class of problems. Now I'm going to tell you that it is for fraud. And so what we did was we tried lots of different approaches. We tried a boosted tree, so just a classical machine learning approach, very good, just to give us sort of a ground benchmark to compare against. And we tried feed-forward networks, very easy model to create. And for both of those, we used atomic, meaning we just took one transaction. Just one transaction, we looked at it and did a prediction of whether or not it was fraud or not. With the LSTMs and the convolutional networks, what we did was we used a sequence of transactions. And we were looking at the sequence of transactions leading up to fraud to see if we can predict that a behavior that was going to indicate that it was fraud. You can actually do that with the feed-forward network as well if you just flatten out all the transactions as inputs, but it didn't work quite as well as the LSTMs and the convolutional networks. I feel obliged to show this slide just because it's kind of novel. What we did here was we took the key features of transactions and then the sequence of transactions, and then we laid them out in a two-dimensional space so it looked like an image. And then we used a convolutional neural network, which is typically used for detecting objects in images. And so now we have a 2D space like an image, and we use the convolutional network to find patterns and anomalies. And this turned out to be actually quite effective. I'm not going through all the details, but what we actually did was we took different features, as you can see, x0, x1, x2 to x9, and then we identified highly correlated features and surrounded those core features with those, and then we kind of laid out the transactions. So intuitively, what you're doing is you're applying filters, and I'm not going to go into too much details about how convolutional neural networks work, but basically you have a filter that's going through and it's looking for patterns in things that are related, be it transactions or features. And just a summary of the general results, the deep learning models did perform better, especially the LSTM convolutional because of the transaction history. And anything with any of the atomic models really just didn't perform much better than machine learning XGBoost. So it really was the sequence of transactions that was giving us the lift, and the deep learning models being able to identify those patterns. I kind of realize we have 20 more minutes, right? I'm probably going a little bit too slow, so I will maybe I'll pick up the pace a little bit. Here's the ROC curve. The blue line is machine learning, and the other lines above that were the deep learning models, and the point is the rules engine. And as you can see, much more a larger AUC for the deep learning. There's also this very nice incline right at the low positive rate. At a low false positive rate, which is something that we want to see. Worth noting that this is actually downscaled data. So the false positive, true positive rate would actually be a little bit different, but it's good for comparisons. One thing we did see as well is that, and I kind of touched on it before, is that the rules engines were good at detecting a certain type of fraud, and the machine learning was good at detecting other types of fraud. And really, the rules engine was good at detecting global patterns that are static, and then the machine learning we used to detect sort of emerging patterns. And it's also useful to think about, you train your model, for example, well, I'll get to this as well, but you might train your model looking for units of fraud, but things to consider is actually the dollar value. At the end of the day, you want to stop as much dollar value of fraud as you can. So that's also something that you kind of need to think about. And as the case is, rules engines might be stopping the larger ticket items, whereas the machine learning models are able to stop a lot more units of transactions, but they're smaller. Anyhow, by combining them both of them together, so basically augmenting your rules engine with say a deep learning score gives the best results. So a fair bit of data prep and preprocessing. And so just to kind of go to my earlier point, we think about deep learning and not requiring feature engineering, and it's generally true if you're doing something like object detection in an image. But when you're doing other types of problems where the data is not uniform, you still need to do a fair bit of data prep and preprocessing. So things that we did was integration. So we needed to take the transactions. You might have other records that indicate whether or not the transaction's fraud or not. You need to integrate it with the customer. You might have auxiliary information about different customers. You need to integrate that all together. And then you might want to take out some of the transactions that your authorization system is easily able to block, like if it didn't have the right CVS number or date, or expiry date, something like that. And then you might want to train your models on different types of scenario. Card present, card not present. You could even more specific. The card is an EMV card, whatever. You do some feature importance. This is really valuable in order to try to identify data leakage. So if you have a massive amount of data, surprisingly, we'll touch upon that a little bit more later. And then you got to do standard data preprocessing. So for those who are familiar with training deep learning models, you know that you can't just put in a categorical variable into a deep learning model because the model will learn something about that number, which is not the point. So you need to use something like one-hot encoding, where you take all your categorical variables and you just have a 1 or a 0. Or some sort of embedding. I'll talk about that a little bit more. And then you still need to do some feature creation, because some things just are not going to work as an embedding. You're not going to do an embedding layer for, say, a postal code, but there might be some important information there. So you might want to change a postal code into, say, a lat long. So, or you might want to know, how far away was the person from the fraud? How far do they live? Things like that. So you're still going to want to create some features. And then there's the data skew problem. When there's a big problem, but there's still a fraction of the transactions are actually fraudulent. It's kind of difficult to train a model with such a small percentage of your actual true positives or actual frauds. So when you train, you probably want to skew the data, maybe 50-50, maybe you want to go to 80-20. So you got data preparation in order to create that. And then, of course, you got to create your training, your test splits. I'm gonna go through. I got a bunch of slides here, so I'll probably stop maybe in about 10 more minutes, and then I'll open it up for questions in the remainder of the time. Another big challenge with using machine learning for detecting fraud is the gap. And so I kind of talked about the global fraud patterns as well as the emerging patterns. So ideally, you would have a model trained on data that you can put into production the next day, right? Let's train on the most recent data and put it into production. Well, you can do it in training because you have all the data there. But it's not reflective of how you're going to put it in production, because when do you know whether or not a transaction is fraudulent or not? Either someone calls up and says, hey, I got some fraud here, or no one calls up. So there's a bit of an aging process. So there's actually a gap that you need to put in between when you train and when you test. And so we call that the gap. Does that make sense? So if you want to go and test in July, you can't use June data because in actual fact of production, you won't know if that was fraudulent or not. So to get actual labeled data, you need to go back to May, for example. You could do a little bit of something and say, hey, well, you know what? In 2 weeks, I probably know 80% of what's fraud. And then I'll go, okay, so maybe I'll do a 2-week gap. So maybe now you might be able to catch trends faster, but you're going to have noise in your data because some of those transactions you think are not fraud, well, 3 weeks later the customer calls it is fraud, so you're introducing some noise in your data. Anyhow, different options there. A rock just hit my wife's windscreen, so I'll just call her later. Detection and the target. So there's different kinds of targets you might want to go for here. And for example, first instance fraud, or second or subsequent fraud. And the reason why this is kind of relevant is if you're using transaction history, then it's important how you assemble that transaction. If you're detecting first instant fraud, so this is the first time the person's committed fraud, then I'm gonna put together my transactions with all non-frauds. But if it's subsequent frauds, I might not have to have such a strict rigor on that, and I might just put in whatever the first 6 transactions. Anyhow, depending upon what type of fraud you're trying to detect, you need to think about how you're going to assemble your previous transactions. And then training and evaluation. One of the things that we found incredibly useful was using Lime and SHAP, and these are these interpretability open source packages. And what that enabled us to do is kind of in that process of training and evaluating the model and reevaluating, we were to look to see which particular fields were most indicative of fraud. And when we looked at that, we were able to figure out things and just kind of make sense. Obviously, in a project, the first thing you want to do is understand your data. So you do as much analysis as you can. You might do some feature analysis of it. Nevertheless, you start building models and you find out, okay, well, this is the most important. Why is this the most important? And then you can go and do a little bit more analysis and find out that maybe you've got some data leakage. Hyperparameter tuning. We did a lot of work in trying different things that we thought intuitively would be the right parameters for the model. But in the end, we used automation to go and just do a hyperparameter sweep. So basically, it automates the process of trying a whole bunch of different parameters for your model to find the best results. And then, something else to think about is and ideally you can probably do that, automate it now. In fact, I think one of my points I made in the keynote, which I think was probably the most important point, was if you do the data preparation properly, if you've integrated your data and you've preprocessed it properly, then really the process of finding the right architecture and the right parameters can be automated relatively easily. Different metrics for thinking about. As I said, you could use the instances of fraud and so true positives and false positives. But more important is the dollar value. So you could also train your models not just looking at the instances of fraud, but actually the dollar value of the fraud, and then train the model to potentially stop the higher level frauds rather than the $20 frauds. Or another thing to consider about is the dollar value fraud prevention over the existing. So if you're using, say, a rules engine, you might want to train your model to find fraud that your rules engine isn't capturing. So again, different kind of training, different kind of data preparation to take those transactions out. Other complexities might be, I don't know how much time we have. Other complexities could be things like if you're trying to identify first-time fraud, I don't know if how detailed you guys want to be about this, but if I'm trying to detect first-time fraud, then if there's a subsequent fraud and I don't detect it, is that a false negative? Well, not really, because I'm training my model to capture the first fraud, so you should probably take those things out. anyhow, another interesting thing that we haven't done, but it's sort of the next step in some of the work we've done, is to think about the loss value function. So all we've done now is we've been training the model with an error rate that's around true positive, false positive, or the dollar value, but what about customer satisfaction? That's another huge thing. So we could actually build neural nets to have a different loss value function to take those other things into consideration.
You've got 10 minutes, Holly.
10 minutes, okay. Embedding layers. So not going into details, but with categorical variables, you can't input that into a model, so you're either going to one-hot encode it, or you're going to use some sort of embedding layer. And basically what an embedding layer is, you have a vector space. So in this example, we're taking dogs, spoons, scissors, cats, and we're trying to create a representation for those using a vector dimension of 3. And basically, we come up with 3 values that we've trained the model to represent. Interestingly, what can happen here, you got to be careful, is you might have variables where the neural net is actually able to learn, or a combination, specifically who the person is, which just sounds great, except that if you go into production again, memorizing in your training set who the fraudster is isn't going to be useful, because when you go and you put that into production, a month later, that fraudster is going to be shut down by then. So your model is actually ending up learning something that's not useful, and actually you want to remove that so your model is actually learning trends that are kind of useful, which is whatever those trends are. Model ensembling. So what we've seen is that there's lots of opportunity to build ensembles of models. So I kind of talked about first fraud and second fraud, or even noisy training, where you have different types of. Don't remember what noisy training is, to be honest. But so your ensembles of models of different time horizons. You can also train your model. If you're just doing atomic, you might train it off of 3 months versus training off of 12 months. And the point there is that you might be finding longer-term static type frauds versus lower frauds. You can also, or shorter period frauds. You can also train it to detect different models for different scenarios. You might have a particular model to go and detect card present, and another model to do card not present. And then building a classifier that then can be trained to go and identify what's the right model to use at the right time is probably the most effective way. You could also try different architectures in there, or different features as well. Sometimes you might want to go and train a model highly focused on the merchant data. Operationalizing, so this is the biggest challenge, and what we've seen working and talking to customers all the time is it's relatively easy to train a model, and you've got things like MXNet and PyTorch and TensorFlow. It's easy to train a model these days. It's a different process in order to put into production, and things that you need to be able to do is like the real-time data integration and preprocessing. So I train my model, I'm using transactions, I have records of what's fraudulent, not fraudulent, I have customer information, and I put that together. I need to do that exact same integration when I go and do inference or score a new transaction coming in. So in real time, when I get a transaction, I need to get all those sources of information that I used in my training to then go in my inference. I need to do it in real time. Same thing with preprocessing. I need to be able to take the data and be able to pre-process it in real time. So change it into one-hot encodings, go do a lookup and find the embedding and put that into the scoring. So there's a couple of options to do this, the pre-processing. I can have the same pipeline that I use for integration and just try to run that. Or you can use feature columns, which is part of the estimator API, and you can put some of that information right into the graph, which will be faster. Anyway, so there's some options there, but you do need to consider, especially if it's going to be doing some sort of real-time authorization, or if you're going to integrate it into something that's doing real-time authorization, you need to be able to figure that out. And then you need to be able to sum the transaction history. So if you say you have a window of 7 transactions that you're looking at, well then when you come time to do inference, you need to get those transactions again. You probably want to cache them. You probably cache the last 6, and then you get the next one and just update that cache. Then you score the transaction, and then you need to integrate it with your rules engine. Like I said before, you're not replacing the rules engine, you want to augment it. So different options there. You could create a score, and you could pass it to the rules engine. You probably have rules like if this, if that, and that's just one element of that to decline or approve. Other options would be let the rules engine do as it does, and then when you come back, you compare that to our score and say, okay, that's all very good, but my score says this, so I'm going to decline it. Anyways, different options there. Running out of time, which is too bad because this is probably one of the most important parts of the whole thing, which is how do you operationalize it and put it into production. Being able to train is one thing. Even to be able to deploy a single model, much more work because you've presumably solved the integration challenges. But the next step is to do the monitoring and retraining and redeployment, right? The whole point of the machine learning models was that we were going to be able to find emerging trends. Well, the models go stale and you need to retrain them because the fraudsters keep on training. And there's no point in monitoring a model if you can't deploy a new model relatively quick. If you've got a 6-month process to deploy a new model, it's not going to be very useful, right? So there's a lot of work that needs to go into this. Ideally, you're going to have some sort of framework that's going to allow you to keep track, some metadata that keeps track. Here's my architecture, here's my weights, here's what I trained it on, here's what I tested on, all in one place. And then ideally, you're going to be able to have some sort of, and I'll just kind of, I'm not going to show this whole architecture. We're kind of running out of time. But ideally, you'd have some sort of framework that allows you to do that and be able to, like, in one button, go and say, okay, let's validate how the model's working, okay, so I can compare it, some sort of champion and challenger, and then that goes off to a workflow, because then you're going to have business stakeholders who want to see it. Okay, all right, well, how's this model compared to this one before they give approval? And then you want to go and then actually put that into production. You might have some sort of scoring services where you're going to have to update in order to do all that integration and preprocessing, which we talked about. Then you want to put that model into a serving environment. Then here, obviously, it needs to be scalable. It needs to be fast. And then in the far corner there, I have a data science workbench. You want to do all of this and not limit what your data science can do. You don't say, okay, we have a governance framework and we've really reduced the time to deploy a model, but now you can't use these tools. So you want to be able to provide them the right tools, the tools they want to use, the flexibility, and know that from the beginning, as they go into production, they're already kind of pre-governed. Just a couple more words. It is a collaborative effort. If you're doing an initiative in your own business and to detect fraud, it is a collaborative effort. You need the business process experts, you need the data custodians who understand your data, someone who understands the rules, you need someone to support the lab, you get your machine learning, your deep learning, the data engineering to do all that data integration and processing, and someone to lead the project. So, key takeaways. AI can significantly improve upon your rules-based fraud detection. A large amount of the work is going to be in pre-processing and preparing the data. That's probably the biggest point. Training models is easy. Preparing data to train models is the challenge. And finally, building an analytic ops capability is probably going to be important in order to support ongoing monitoring and retraining, which is critical in the fight against financial crime. That's it. I got a few minutes for questions. Yes?
Did you guys try out auto-encoders?
Yeah. Yeah, actually we did. And so, and just for everybody, or for me too, you're talking about what we could do is we could take an autoencoder and get it to be able to see what a good transaction looks like, right? So it goes in the autoencoder, we get a representation, and then we span it back out again, and we look at the output. And there should be a little bit of error in between those two inputs and outputs. So now we have an autoencoder that can reproduce good transactions. So now we take a bad transaction, we plug it in, it shouldn't work. The error should be larger. We did try that. It didn't work as well as some of the other approaches. And I think maybe it's probably because, and I think there's a lot of areas to do in this area, more work that can be done in this area, but what we saw was the transaction history was really important. So what I've just described is sort of an atomic autoencoder, if you would. something that might be interesting would be a autoencoder that takes a series of transactions. So to learn a series of transactions and then try to do that, but we haven't done that kind of work.
In your description, in your session description, you mentioned about account takeover mitigations, right?
Yeah.
So did your models that you just put here in the session, did they address account takeovers?
No, they didn't. That's a good question. I probably should have spent a little bit more time kind of talking about the different types of fraud that are involved. You have third-party fraud, you've got first-party fraud, and sort of that kind of stuff is more of the account origination problem and synthetic identity. We didn't do as much on that. What I was talking more about was, fraud that happens, transaction fraud. Yeah.
Transaction in a banking, traditional banking system or credit card or what?
Credit card and banking, yeah. And online payments.
Another question.
Yeah.
When you take, pieces of data that is like, raw transaction can be read and move it to images.
Yeah.
And then eventually you want the human to maybe check it out.
Yeah.
Checking an image visually is, okay, but it doesn't give the person this, confidence saying, yes, this is fraud.
Yes.
Where a proper rule system, you can show the proper rules and you give that. So how do you, you took a kind of simple problem, made it harder for a human to understand.
Yeah. It is an excellent point, and just to broaden it, whether it's a convolutional network or anything, you have hidden layers. It's not as easy to look at a mess of nodes and say, okay, that's what's happening, as you would a decision tree which says, okay, well that's the thing that fired it. That's where these tools like LIME and SHAP come into play.
LIME and
SHAP.
chat.
Yeah, SHAP. So they are tools that, without going to the details, they kind of perturb the different inputs and, kind of rerun it so you can see which inputs, were causing it to come up with the prediction that it did. It's not foolproof. It's still a bit of a process, to be honest with you, because, some of those features are going to be fairly esoteric. So, it still requires some work. But there is stuff that you can do. It's a bit of a, yeah. Yeah.
I have a simple question. So can you explain more details about how can you transform the sequence of transaction to an image on your slide? Because I'm confused.
Yeah, sure. I go back here. So what we did was we did some feature analysis, and we picked out some of the most important features in a transaction. And then we also looked at what features they were correlated with, so just basic statistics. And then we laid out on the x-axis each one of those features surrounded by the features that it was highly correlated. I'm getting the times up, so I guess I'll just keep on going until someone kicks us out, or am I done?
Well, you got a couple more minutes.
Couple more minutes, okay. So we laid that on the x-axis, and then we did the same thing for each of the transactions that happened prior to it. That's how we create the two-dimensional image. I'll go her, then I'll do you both, yeah.
I'm just curious, can you give us an example where you did a bad transaction or a good transaction? Like any feature which is more prominent and vivid most of the time? Any example which you can share with us?
Of the different features?
Of a bad transaction, like how you identify between a good and a bad transaction? Yeah.
How do you identify between a good and a bad transaction?
Yeah. From the case studies, like what you have seen in bad transactions, which made it bad.
All right, with some of the core features? Oh, well, yeah. There's a range. I mean, yeah. Well, we could talk about that later, maybe.
All right.
What's your quick question?
Yeah. So in comparison to the neural networks
Yeah.
and the traditional, ensemble methods and machine learning,
Yeah.
have you considered, or as part of your analysis, did you think about the whiteboard recurrence or probabilistic graphical models or Markovian models in comparison to how it fared with the neural networks?
I think there is a lot of opportunity to combine neural nets with some of those graph approaches, which we haven't done.
Thank you.
All right. Okay. I think my time's up. I'll ask your question afterwards if you want.